right, today we're going to look at the derivatives of the trig functions and the derivatives of the inverse trig functions. So here I have all the formulas, and so we're just going to go ahead and look at the examples in your notes. So keep this handy as we go through those. All right, so let's get started. First example we have is y equals x squared times sine of x. So because these two are being multiplied together, we would use the product rule. So as we start, y prime equals the first, which is x squared, times the derivative of the second. The derivative of sine is going to be cosine of x. So we've got first times the derivative of the second plus the second, which is sine of x, times the derivative of the first, which is 2x. Now, if I clean this up a little bit, then this is going to clean up to be y prime equals x squared times cosine of x, or just x squared cosine of x, plus I'll swing the 2x in front of the sine of x, and there we have it. Y prime equals x squared cosine of x plus 2x sine of x. All right, so that's the first example. Our next example, if you notice, is going to involve the quotient rule. We have y equals cosine of x over 1 minus sine of x. So remember yodeling, low-de high minus high-de low over low-low. So y prime equals, I'll take the low, which is 1 minus sine of x. I will multiply it by the derivative of the high, and the derivative of cosine of x is negative sine of x. So I've got low d high minus high, which is cosine of x, times the derivative of low. And when you take the derivative of 1, that is 0, so we can get rid of that. You still have your minus there, and the derivative of sine of x is cosine of x. And so now all of that, don't forget, is over low, which is 1 minus sine of x squared. So walking through this one more time, we have low d high minus high d low over low. So when I go to clean this up, I'm going to distribute here. 1 times negative sine of x is negative sine of x. Multiply negative sine of x times negative sine of x, and we get positive sine squared of x. Now I'll move over to negative, or subtracting cosine times negative cosine of x. Well, this negative times this negative makes that positive, and cosine of x times cosine of x will be cosine squared of x. And all of that is over 1 minus sine of x squared. Now, if we go back to pre-calculus, when we were working with trig functions, we worked with identities, and there was an identity that we worked with that said sine squared x plus cosine squared x equals 1. Well, because sine squared x plus cosine squared x equals 1, then sine squared x plus cosine squared x can be replaced with 1. So now what I have is this negative sine of x. I will replace sine squared x plus cosine squared x with 1, positive 1, and that's all over 1 minus sine of x squared. If I turn the numerator around, I can rearrange the numerator to be positive 1 minus sine of x, with that being divided by 1 minus sine of x squared. This now can be reduced to y prime equals, the 1 minus sine of x is a binomial. My 1 minus sine of x squared is a binomial squared. And because the two binomials are identical, they can be canceled, and you're left with 1 on top divided by 1 minus sine of x. So there's your derivative of y equals cosine of x over 1 minus sine of x. Ends up being y prime equals 1 over 1 minus sine of x. All right, so moving on to the next example. Now we have y equals cosine of x plus 1. This is going to be where I think a u substitution might be beneficial. So I'm going to let u equal, is that on the page? Yep. X plus 1. I know that I will need u prime, and the derivative of x is 1. So now I'm going to rewrite this in terms of u. So I have y equals cosine of u. Now I will find the derivative, and that would be y prime equals the derivative of cosine is the opposite of sine of u, and I still need to I have to multiply that by u prime. So now it's just a matter of going back in and replacing u with x plus 1 and u prime with 1, which leaves me with y prime equals the opposite of, or negative, sine of x plus 1 times 1, which we could just leave off, and that would be y prime equals the opposite of, or negative, sine of x plus 1. Okay, so the u substitution, using a u substitution is going to be helpful when dealing with trig functions as well. So moving on to our next example. So this time, let's let u equal 3x squared. We know that we will need u prime, and so the derivative of 3x squared is 6x. So now I'll rewrite y equals cosine of 3x squared as y equals cosine of u. The derivative then will be y prime equals the opposite of sine of u times u prime. Now let's just go back in and replace our u and u prime, and we get y prime equals negative sine of 3x squared times u prime, which is 6x. Now, 6x does not get multiplied by 3x squared. But what we can do is take that 6x and bring it out front and make it a coefficient, maybe. So that would be negative 6x times the sine of 3x squared. Okay, now for the next example, tangent of 3x. Let's let u equal 3x, and therefore u prime will be 3. So now what I have is, when I rewrite this in terms of u, I have y equals tangent of u. The derivative of that then will be secant squared u times u prime, and therefore replacing u and u prime with their 3x and 3, we end up with y prime equals secant squared of 3x times 3. And so y prime then would equal 3 times the secant squared of 3x. All right, so moving on to our next example. This is going to, let's let u equal the quantity 3x squared. This is going to be very similar to the last example, but when finding the derivative of 3x to the second power, you are going to use the chain rule on this piece right here. So the derivative of the quantity of 3x squared will be 2 times 3x to the first times the derivative of 3x, which is 3. And so that turns out to be 2 times 3 is 6, and 6 times 3 is 18, so that's 18x. So when I go back to rewrite this in terms of u, it ends up being y equals cosine of u. So y prime is going to be negative sine of u times u prime. So y prime equals the opposite of, sine of, I'm going to replace u with 3x to the second power. Multiply that by u prime, which is 18x, and y prime equals, I'm going to swing the 18x out front, and that would be negative 18x times the sine of 3x squared. Now, this is not necessary, bringing the 18x out front is not really necessary, but if this were a question on a multiple choice test, you would need to be able to recognize that this expression and this expression are equivalent. Okay, so just kind of keep that in mind. All right, so now let's take a look at our next example, y equals cosine squared of x. So this particular example, I'm going to rewrite first as y equals cosine of x all squared. From Trig, we learned that cosine squared x is the same thing as cosine of x squared. So if you want to use a u substitution, then this time I'm going to let u equal cosine of x. I know I will need u prime, and the derivative of cosine is negative sine of x. And now I can rewrite this expression, cosine of x to the second power. I can write that as u squared. All right, so when I find the derivative in terms of u, we will have y prime equals 2 times u, or 2u to the first, times u prime. So replacing u with cosine and u prime with negative sine, I get 2 times cosine of x times negative sine of x. And so cleaning this up, I'm just going to bring the negative out front, and I have negative 2 cosine of x times the sine of x. And from pre-calculus, there is an identity that is 2 cosine of x sine of x. And that identity is the double angle identity for sine. So from pre-cal, sine of 2x is equal to 2 sine x times cosine of x, which is equivalent to this. If this, I'm sorry, let me pull that over. So sine of 2x is equal to 2 sine of x cosine of x, which is this expression right here. If this were a multiple choice question, you would need to maybe be able to recognize, you would probably need to recognize that 2 cosine of x sine of x can be replaced with sine of 2x. And so your derivative may be in the form of y prime equals negative sine of 2x. All right. Sorry about that. Let's move on to our next example. This example is very similar to the last example in terms of you've got this sine cubed of 4t. And I would rewrite this first as y equals the sine of 4t to the third power. And so I'm going to let u equal the sine of 4t. We will need u prime. And here we're going to have to actually use the chain rule on this expression. So the derivative of sine is cosine. So the derivative of the outside, which is sine, will be cosine of 4t times the derivative of 4t, which is 4. So u prime is going to be 4 times cosine of 4t. Thanks. Okay, so now when I rewrite this original equation as y equals the sine of 4t, I'm going to replace with u. This would be u to the third. The derivative of this in terms of u will be y prime equals 3u squared times u prime. And so I will now replace my u and the u prime with their counterparts, x counterparts, and we get y prime equals 3 times, okay, my u is sine of 4t squared times u prime, which was 4 times cosine of 4t. So if I clean this up a little bit, I can multiply my 3 times this 4, and I get 12 sine of 4t squared. If I put it back in its original form, it would be sine squared of 4t times the cosine of 4t. Okay? So we're just utilizing the derivative rules that we've learned in previous lessons, previous units, but now we're incorporating the trig functions as well. All right, so a couple more. Let's move on. So now let's take a look. We have y equals the secant of 2x. I'm going to let u equal 2x. The derivative of u prime, will be 2. If I rewrite this in terms of u, my equation then is going to be y equals secant of u. And to differentiate this, we end up with y prime equals, now the derivative of secant of u is secant u times tangent of u times u prime. And so now let's just go back in and replace u with 2x, u prime with 2, and we end up with secant of 2x times tangent of 2x times 2, and y prime, if I just pull the 2 in the front to make it the coefficient, that would be 2 secant of 2x times tangent of 2x. So hopefully that gives you a little practice just working with finding derivatives involving trig functions. So now what I want us to do is I want us to look at some examples that involve implicit differentiation involving the trig functions. So our next example we have is sine of x plus y equals y squared cosine of x. So for this example, I'm going to find the derivative of the left side and the derivative of the right side. So here I have to use the chain rule on the left side. So that's going to be the derivative of sine is cosine. So I have cosine of the stuff, x plus y, times the derivative of the stuff. So what's the derivative of x? That would be 1, plus what's the derivative of y? That would be y prime. Now on the right side, we will find the derivative using the product rule, because y squared is multiplied by cosine of x. Okay, so the derivative of y squared is going to be 2 times y to the first times y prime. That's, oh, I just told a story. Let's back up a minute. That's not right. Okay, believe I said we needed to use the product rule. So the product rule would be first, which is y squared, times the derivative of the second, which is negative sine of x, plus the second, cosine of x, times the derivative of the first. Now we have 2 times y to the first times y prime. Okay, this is pretty nasty, but ultimately when you're finding the derivative, when possible, you want to get y prime by itself. So I need to do some cleaning up. Here I'm going to distribute, but I'm not distributing the x plus y onto 1 plus y prime. I'm distributing cosine of x plus y onto 1, and then cosine of x plus y onto y prime. So what will that look like? Well, it's going to look like this. Make sure I'm still on the page. So cosine of x plus y times the 1 plus, I'll do this, plus cosine of x plus y times y prime will be y prime times cosine of x plus y. Now on the right side, the first term here, I will write it as negative y squared sine of x plus, I'm going to put the y, I'm going to put 2y y prime in front of cosine. So 2y y prime cosine of x. So now it's a matter of, we have this term that has a y prime, we have this term that has a y prime. These two terms do not have a y prime. So I want to get the terms with the y prime on one side and the terms without on the other. So I'm just going to add the y squared sine of x to the left. So that means I have cosine of x plus y squared sine of x equals. Now I'm going to keep my 2y prime cosine of x on the right, and I'm going to subtract y prime times cosine of x plus y to the right. Now, if you remember, to get y prime by itself, or to isolate y prime, we have to do some factoring. So I will factor y prime out of these two terms. And when I do, I'm left with 2y cosine of x minus cosine of x plus y. All I did was factor the y prime out of these two terms. And over here on the left, I still have cosine of x plus y squared sine of x. And then all I have left to do to get y prime by itself is to divide both sides by this expression. So I'm going to divide both sides by this, and I will be left with, I like my y prime on the left, equals cosine of x plus y squared sine of x over this stuff, 2y cosine of x minus cosine of x plus y. And there is your derivative, or y prime. Okay? All right, so good old implicit differentiation. All right, so next example, very similar. I just need to do the same thing. Implicit differentiation. I'll work with the left side. I will also work with the right side. So, derivative of the left. The derivative of 5y squared will be 10y times y prime plus the derivative of sine of y is going to be cosine of y times y prime. Remember that variable is y, just as it is here, so you have to multiply by y prime. Okay, then that will equal the derivative on the right is going to be 2 times x. So now it's just a matter of isolating y prime. Let's get y prime by itself. So that means we have to factor y prime. And I will multiply by 2y plus cosine of y equals 2x. And now all I have to do to get y prime by itself is to divide both sides by 10y plus cosine of y. So y prime equals 2x over 10y plus cosine of y. All right, so that gives you quite a bit of practice finding derivatives that actually involve the trig functions. Our next example that we will go through is going to be taking the derivatives a little bit further, writing equations of tangent lines, or actually finding the values where a function has a horizontal tangent. So let's go ahead and get to that example. So here we have f of x equals secant of x over 1 plus tangent of x. And the very first thing that we are asked to do with this for the a portion is to find f prime of x. Okay, so that means find the derivative of f. And because because f is secant of x over 1 plus tangent of x, we're going to have to use the quotient rule. So low 1 plus tangent of x times the derivative of high, which is secant x tangent of x. So it's low d high minus high times the derivative of low. The derivative of 1 is 0. The derivative of tangent is secant squared x. So I have low d high minus high d low over low. 1 plus tangent of x squared. Okay, so this is the very raw form of the derivative. Looking ahead to Part B wants us to find for what values of x does the graph of f have a horizontal tangent. Well, remember, what helps us find horizontal tangents? Well, a tangent line is horizontal. When a tangent line is horizontal, that means the derivative is 0. So that means we want to take the derivative and set it equal to 0. So that means I need to do some cleaning up of this derivative. So what I'm going to do is I am going to let's do this. If I distribute here 1 times secant of x tangent of x. That gives me secant x tangent of x. And when I multiply tangent of x by secant x tangent x, that gives me plus secant of x tangent squared x minus secant cubed x. When I multiply secant of x times secant squared x, I get secant cubed x over 1 plus tangent of x all squared. Okay, so, if I go ahead now and set this derivative equal to 0, let me scoot that over, sorry. Okay. Then when I start to solve this, all I really am interested in is the numerator equaling 0. Because if you were to treat this as 0 over 1 and you did the whole cross multiplying business, all of this multiplied by 1 gives you secant x tangent x plus secant x tangent squared x minus secant cubed x equals, when you multiply those two together, you get 0. Okay, so what we should probably do now is this. I would say, what do all three of these terms have in common? They have a secant. Let's factor it out. So secant of x times, I have tangent of x plus tangent squared x minus secant squared x equals 0. So this secant squared x, I factored, the secant squared x is a result of factoring a secant out of secant cubed. Now, if I go back to my identities for secant squared, there is a Pythagorean identity that tells us that tangent squared x plus 1 equals secant squared x. So what I can do is I can take secant squared x and replace it with tangent squared x plus 1. And that will give me all of this in terms of tangent. So this is what this is going to look like. Secant of x times tangent x plus tangent squared x minus tangent squared x plus 1. And what we always have to be careful with is this subtraction here. I replaced secant squared x with tangent squared x plus 1, and that means I've got to subtract all of that. So I'm going to rewrite this as secant of x times tangent x plus tangent squared x minus tangent squared x minus 1, and all that still equals 0. And then if I look inside here, my tangent squares cancel, and I'm left with secant of x times tangent of x minus 1 equals 0. So what we did is I've taken this numerator and factored out secant, cleaned this up by replacing secant squared with tangent squared x plus 1. And basically what I've got is secant of x times tangent of x minus 1 equals 0. So here I have a product of two nice factors. And when the product of two factors equals 0, then either secant of x equals 0 or tangent of x minus 1 equals 0. So now we have to go back and think, okay, is there any angle measure where secant is 0? And the answer to that is no. Is there any tangent value, well, if I get tangent of x by itself, then tangent of x equals 1. Is there an angle measure for which tangent equals 1? And the answer to that is yes. At pi over 4, and then again at 5 pi over 4. So tangent of x minus 1 equals 0. Tangent of x equals 1, so x will be pi over 4 and 5 pi over 4. And what does that mean? That means that f has horizontal tangent lines at x equals pi over 4 and 5 pi over 4. So we had to find the derivative. We had to find the derivative of f. And in cleaning up the derivative, we needed to identify where secant of x was 0, which there is no angle measure. Remember, x represents an angle measure. There is no angle measure where secant is 0. And we needed to find where tangent of x minus 1 equals 0. And we found those to be at pi over 4 and 5 pi over 4. Just as a little reminder, remember the ordered pairs for the pi over 4 angles are square root of 2 over 2, square root of 2 over 2. Therefore, tangent is positive 1. So, f has horizontal tangent lines at x equals pi over 4 and 5 pi over 4. All right, so that one was a little involved. Now, the next few examples are just going to give you a little idea of what the derivatives of the inverse trig functions look like. And these are going to go pretty quickly, and then this particular lesson will be done. So, the inverse trig functions. Make sure you have your copy of your trig functions, your inverse trig function derivatives handy. One thing I do want to point out is anytime you see something like arc cosine of x, oops, let me scoot that over. That is the same thing as inverse cosine of x. Okay, so just kind of keep that in mind, because the phrase arc, or the notation arc cosine of x, is used about as often as this notation inverse cosine of x. So they mean the same thing. So here's our first example. I'm going to use a u substitution. I'm going to let u equal 2x. That means u prime is going to be 2. The formula for finding the derivative of the inverse sign is u prime over the square root of 1 minus u squared. So the derivative then will be 2 over the square root of 1 minus, my u is 2x, and I have to square the u. And so that really just turns out to be 2 over the square root of 1 minus 4x squared. There you go. All right. Next one, another u approach. I'm going to let u equal 3x. We will need u prime, and that will be 3. So the formula for finding the derivative of the inverse tangent, I'll go ahead and write it right here. Inverse tangent is going to be u prime over 1 plus u squared. So now u prime is 3 over 1 plus our u is 3x. I'll square that, and that cleans up to be 3 over 1 plus 9x squared. All right. So those are two kind of nice, neat, clean versions or examples of finding the derivatives of trig functions. Let's look at our last one. And if you've looked ahead at the notes, This one is a little bit more involved, but it's just a matter of sticking with it and persevering. So let's let u equal the square root of x, which again is the same thing as x to the 1/2. U prime. We know we need u prime, so the derivative then will be 1/2 x to the negative 1/2. All right, the derivative for the inverse of sine is u prime over the square root of 1 minus u squared. All right, so here's what we've got. U prime. U prime is 1/2 x to the negative 1/2, and all of that is over the square root of 1 minus u, which is x to the 1/2 squared. Okay, so as I go about cleaning this up, this x to the negative 1/2, I'm going to ignore the denominator for just a minute, but I can rewrite 1/2 x to the negative 1/2 as 1 over 2x to the positive 1/2 power. And all of that is divided by the square root of 1 minus, now remember, x to the 1/2 raised to the second power, when a power is raised to a power, you multiply. That gives you x. So now what I've got is this. 1 over 2, I'm going to rewrite x to the 1/2 as the square root of x. Now, if you remember, this denominator could be written as over 1. So instead of dividing, I can now change this to multiplication. Let me scoot that over, sorry. And I will have 1 over 2 on the square root of x times the reciprocal of this. So 1 over the square root of 1 minus x. And folks, we're just going to leave this as 1 over 2 on the square root of x times the square root of 1 minus x. So that concludes the examples for lesson 1, the derivatives of trig functions and the derivatives of the inverse trig functions. So the good thing is if you need to, you can always pause wherever you need to. I know I've kind of talked pretty quickly, but yet this is still a pretty lengthy video. But I hope it has helped. If you have, run into some scenarios on your assignment that has been provided, and you go through the answers and you're still not exactly sure, what's going on, please don't hesitate to reach out. I'm here to help. So until lesson 2, I'll see you next time.